very efficient.
Newton, you tell us when. I'll change the camera, and Newton, you tell us. Good. Okay, so let's start. Okay, we're very happy to have Alessandra with us today, and she will speak about an ergodic theorem with weights and applications to random measures, random walks, homogenization, and IPS hydrodynamics.
Okay, thanks a lot for this invitation. As I was saying before, I'm not used anymore much to give an online seminar, so I hope that everything will be okay. Okay, I will first discuss about generalized ergodic theorems and then move to the application. So the first part of the talk will be rather abstract, very general in some sense. So I started talking about the ergodic theorem with weights, and I want to recall the multidimensional Birkhoff ergodic theorem, and so this is also an occasion to recall a fundamental concept in ergodic theory, which will be used very much in what follows, which is the action of the group on the probability space. So in my talk, the group G will be RD or CD as additive group, and G is a measurable space with the Borel sigma field. So for CD in particular, the topology is the discrete topology. And okay, anyway, so this is the definition. And now I define the action. So the action of the group G on my probability space, where here F is the sigma algebra of events, is a family of maps, theta G, parameterized by G, the elements of the group. So each theta G is a map from omega to omega, and they satisfy the following properties. So theta of 0 is the identity. Then you have, okay, the group property, theta G composed theta G prime is equal to theta G plus G prime for each G prime in the group. And then you have the joint measurability of theta G omega, both in G and in omega. Okay, and I recall you some standard terminology. So the probability P of...
Alessandra?
Yes?
Just a quick question. So sometimes people ask this property, the group identity, to hold almost surely in omega. For the moment, there's no measure in omega, but
no, this okay. This is you can think pointwise. No, not only almost sure. Okay, otherwise you restrict. But I take this form here of action.
Okay.
Okay, let us say to simplify, but usually it's in this form. Okay, anyway, you can, okay, this is the concept of action. And then the probability is called stationary if each map theta G is measured preserving, which means that for each event A and theta G minus 1, the inverse map of A, have the same probability. And then we can consider the invariant sets. So A is invariant if it is left fixed by theta G in that sense. Okay, and the family of invariant sets is a sigma algebra. You can work also with semi-invariant sets, where this equality here holds with a part measure, so a part set of probability 0, that is these two sets, the symmetric difference, the symmetric difference of these two sets, probability 0, and then instead of this I, you can take the sigma algebra generated by semi-invariant sets. Okay, and then usually P is called ergodic for the action. I use the short notation G ergodic if it is G stationary and the invariant sets have a trivial probability, that is 0 or 1. Okay, and now I recall, just a remark. So when the group G is equal to CD, you can avoid all these abstract setting. Indeed, the actions have a simple characterization. All actions of the group CD on the probability space are of this form. So there are D maps, T1, T2, TD from omega to omega, which are measurable, bijective, and commuting. And then theta G has to be of this form, T1 to G1, then composed with the T2, power G2, and so on, composed with TD, power GD, where G1, G2, and GD are the components of the vector G. And in this case, with the G equal to CD, stationarity means just that the T1, T2, and TD, these basic fundamental maps, are measure preserving. Okay, and I recall you the multidimensional Birkhoff ergodic theorem, which was proved by Tempelman. So let us take the group G equal to CD, and let us suppose that G acts on the probability space by measure preserving maps. So the probability P is G stationary. Then let us take a sequence of boxes, AN, an increasing sequence of boxes invading all CD. And then you have this convergence. So given f in LP, given a function in LP, with P numbers at least one, then the average of F compose theta J with a J in the box, or you can call G if you want. Here I prefer J. So the average of these functions converges to the conditional expectation of F with respect to the sigma algebra of the invariant sets. And this convergence is both pure surely and also in LP. And then Tempelman and his co-workers have, also other people have worked in order to extend these results, for example, by considering more general sets, not only boxes, but they are always bounded in the theorems, also other groups or semi-groups instead of CD. Okay, and let me remark that behind this multidimensional ergodic theorem, there is another theorem at the basis, which is very important too, and it is the maximal inequality. It's this, similar to the Hardy-Littlewood maximal inequality in analysis, and it is also called dominated ergodic theorem, which states, okay, the following: under the same conditions as before, given f in L1, an integrable function of on the probability space, which is non-negative, then for each alpha positive, the probability that the supremum of all these averages, the probability that this is bigger than alpha, is bounded by 1 over alpha times the L1 norm of F, times a constant, which depends on D. Okay, okay, let us a little reflect on this multidimensional ergodic theorem. So let us take the case of AN equal to the box in CD of radius n. So there is, these sets are homothetic, and in particular, if you define the function phi as the characteristic function of the box -1, 1 to D, then the average that appear in the ergodic theorem or in the maximal inequality can be rewritten in this form. So it is equal to 1 over 2n plus 1d, so the cardinality of AN, and then the sum with the J in CD, phi evaluated in J divided by n, so this is a number, times F compose theta J. Okay, and then there is this question coming from the application, but I will show you the application at the second part. So do the ergodic theorem and the maximal inequality that I've shown before, remain valid if we take a test function phi with non-compact support, because this phi has compact support. I'm interested to the case of phi with non-compact support, but somehow decay, so that the right-hand side in this identity becomes more sensible to the behavior at infinity. So, and okay, I had in mind a particular application, and I contacted Arkady Tempelman. So he's old but still active. So he's a professor emeritus in the United States, and then he gave me this this reference. So it's a proposition inside a very robust paper of Tempelman and Schulman of 2019. And the result is the following. Okay, here the theorem is for G equal to RD, but okay, to go from RD to CD and vice versa is not a big pain. So let us suppose that the group G equal to RD act on the probability space by measure preserving maps. So P is G stationary. Now take a function phi, let us consider for simplicity continuous function, but it's more general the result, having a polynomial decay, let us say, so the modulus of phi is bounded by 1 plus the norm of x to minus beta. With beta, the exponent is larger than d. And then we have the following. For any function f which is in LP, and P is a number but strictly larger than 1, we have that this average, so 1 over ND, so it's a generalized average. So I use the term average in a more relaxed way. So 1 over, I don't refer to something which is normalized to 1. 1 over ND, and then you take the integral on dx in RD, of phi evaluated in x over n. So this is a number, you multiply this number with the function f compose theta x. Theta x is the map associated to the action of the group RD. Then this average converges when n goes to infinity to a constant depending on phi, and exactly this is the integral of phi, of the function phi times the expected, the conditional expectation of f with respect to the sigma algebra of invariant sets. And this happens, this convergence is both pure more surely and NLP. So I have simplified a little the version, so the theorem is more technical, but also a little more general. But the problem of this theorem for my applications is that it does not cover P equal to 1. So the method really requires that P is strictly larger than 1. Okay, and now I state, so I worked, and I state now an ergodic theorem with weights for the group CD. They are equivalent to CD and RD for many aspects. Covering the case of P equal to 1. Okay, so let us take, so the theorem is the following. The theorem I produce is the following. Supposed to have the group G equal to ZD acting on the probability space, and suppose that, so it acts by measure preserving maps, so P is stationary for the action. So let us take phi, a function, with a decay, like in the previous theorem of Tempelman and Schulman, but now beta is larger. Beta is larger than 2d plus 2. Before it was only d. And then for each f in LP, and P can be even 1, I have exactly the same statement, but now, okay, the average is on discrete points of ZD. So 1 over ND, and then I sum over J and ZD. The function, so I have a number, the function phi, evaluating J over N, times the function f compose theta J. So this average, generalized average, converges to the integral of phi times the expected value of f with respect to the sigma algebra of invariant sets. This both pure more surely and in LP. And so this theorem has been obtained also by proving before a maximal inequality, which is relevant by itself. Okay, now this is abstract. I wanted to apply this theorem, show an application to something still abstract, but a little more concrete, and then we will arrive to something concrete. So from this result, I obtain an ergodic theorem for random measures on RD. Okay, now let's start. The setting is the following. Okay, so let us start from scratch. Again, I have actions, but now I have two actions because I have RD, which is a space on which I have translations. Okay, again, G is given by RD or ZD, the abelian groups, and let us suppose it takes a probability space, omega FP, okay? And that the action is stationary. But on the other hand, as I mentioned before, the group G acts on RD by Euclidean translation. So let us fix an action. So by Euclidean translations, I mean this. I have a family of translation, tau G, parameterized by the elements of the group, so tau G for each G in the group, and they are of this form. So tau G of X is a translation of X along the vector Vg, where V is an invertible matrix which is fixed. It does not depend on the element of the group. So you can think at the beginning to V equal to the identity, and then tau G of X is simply the translation of the point X along the vector G. Okay, and now let us introduce M, the space of locally finite measures on RD, and also this is a measurable space with the Borel subsets, okay? And we assume to have a random measure. Therefore, I have a map from my probability space associated to omega in the probability space, a measure in M, so mu M, and this random measure satisfies this covariant relation. Now I will show you examples. So I have that for each G in the group, the measure associated to theta G of omega gives mass to the set A, which is equal to the mass given by the original measure, mu of omega, the mass of the translated set, tau G of A. Okay, it can sound strange, but indeed there are plenty of situations where we have random measures with this covariant relation. I show you an example. Okay, so let us consider this example. So example 1. So in this case, the elements of my probability space are so marks simple point processes. Okay, more precisely, a generic element omega of my probability space is a family of pairs xi, ui, where the xi are in RD and ui are number 0, 1, and all the xi form a locally finite subset of RD. So here you can see a graphical representation. So an element omega, my probability space, is at the end just a family, locally finite family of points in RD marked with number. For example, this point is xi, and the mark ui is 0.1. So this is an element of the probability space. Given omega, I can associate to omega a measure, an atomic measure, which is simply the combination of the delta, the Dirac measure on the points xi with the weight ui. And okay, I have to fix a probability on this space. For example, you can think to sample these dot points with a Poisson simple point process, or your favorite simple point process, which is translation invariant in the usual meaning. And then I can mark these red points by IID uniform random variables, just to give an example. And I call P the law of the resulting mark point process. Okay, so P will be the law of my probability space. Now here you don't see groups. You don't see groups, but indeed there are. there is the group with two actions. Okay, in this simple example. So the group underlying this example, so behind this example is RD. And RD acts on the space, on the Euclidean space by the trivial translation. So tau G of X is equal to X plus G is the translation along G. And if you can define a translation of omega, which is a sort of environment, and it's this. So given omega of this form, so with this notation, then theta G, the action of the group G, exacted by the element small g, on omega, is obtained by translating the point xi by tau minus g, and each point keeps its energy marker. So you can check that, so it's simple. P is, so the law I chosen by taking this marker Poisson point process is stationary. So these maps here are left, so are measured preserving for the law. And moreover, the covariant relation I showed you at the beginning is satisfied. I show you another example. Okay. Which is discrete, more discrete. So let us take, for example, the two-dimensional hexagonal lattice, and I called V the vertex set in the two-dimensional hexagonal lattice, which is this black underlying structure here, okay? And then I take as a probability space, so I take as omega the product space 0, 1 to the vertex set of the hexagonal lattice. Therefore, an element of my space is a family of numbers associated 0, 1, they can be 0, 1, associated to the vertices of the lattice. And I can take, for example, on omega as probability, the Bernoulli product probability, exactly as in the Bernoulli side percolation. And then to each omega, I can associate a random measure, which is simply the measure given by, so you take the sum with X in the hexagonal lattice, such that omega X is equal to 1. In the percolation terminology, it means X is open, and then you take a delta, a Dirac measure on X. So you can, it's indeed, when you study simple point processes, for example, and you deal with locally finite sets of points, it is, you associate, it's a bijection to a set, you can associate a measure simply in this way, by associating a Dirac measure of mass 1 to each point. Okay, I just restated the Bernoulli side percolation in terms of random measures. Okay, but here at the beginning in this model, you don't see any group, but there is the group with the two actions, and it's here. So the group is ZD with D equal to 2, so Z2. And now the group X on the Euclidean space by Euclidean translations, but you are not interested, so it's not natural to take all Euclidean translations. So if you watch to this picture, you see that your translations that keep invariant the underlying hexagonal lattice are translations given by along the vectors that are multiple integer multiple of these V vectors V1 and V2. So you are interested to translation which are given by G1 times V1 plus G2 times V2, okay, where G1 and G2 are integer. Therefore, this is the definition. So tau given G in Z2, the tau G, the translation associated to G, is maps the point X into X plus VG, where V is the invertible matrix given by having columns V1 and V2. And then you can define also the action of the group on the probability space. You you have to suitably translate these 0-1 numbers that you associate to the vertices. And then you have that indeed your probability is stationary for the action, theta g, and the covariant relation is satisfied by the random measure I described before, okay? Okay, now in order to state the ergodic theorem for random measure, I need to introduce, a concept which is common, for example, in solid state physics, if you study crystals. So the fundamental cell, okay, recall that G acts on RD by translation, and the translation are of this form, where V is an invertible matrix. And I've called V1, V2, and Vd the columns of this matrix. Then the fundamental cell is a parallelepiped, delta, which is generated by these vectors, Vi. So in particular, in the previous case, the fundamental set in example 2 is this parallelogram. Pay attention that this border is absent because here it is strictly smaller than 1. And in example 1, or in general, if V is the identity, then the fundamental cell is just the unit box 0, 1, 2D. And so this is the concept, this is the fundamental cell. Another important concept is the concept of intensity. So the intensity M of my random measure is given by the average mass assigned to the fundamental cell divided by the volume of the fundamental cell. This is the Lebesgue measure of the fundamental cell. Okay. And so if you have a question, please interrupt me. Okay, now to state the ergodic theorem, so I want to describe the behavior of this of my random measure when I do a rescaling. But I want, I will comment. So sorry, I give comments later. So let us rescale my measure. So I have epsilon, the positive, this is the scaling parameter, and I define the rescale measure in this way. So mu epsilon of omega of a set A is equal to epsilon to D times the measure mu omega of the enlarged dilated set A divided by epsilon. So with this formula, we have this identity. So when you integrate with a function f, an observable f with respect to the rescale measure, then this is exactly as doing the following. You take epsilon to D, and then you integrate f in epsilon x with respect to the original measure. So let us consider an example, something very simple. So suppose that mu omega, for example, is an atomic measure, a sum of Dirac data, so Dirac measures. If mu omega is this sum, then mu epsilon omega is again a combination, a sum of Dirac measure, but now the atoms have been rescaled. So if before you had an atom in X, now you have the atom in epsilon X. And each atom now brings the weight epsilon to D. Okay. And finally, I can state the theorem. Okay. So this the ergodic theorem for random measures. I have to point out, one thing. My random measures. Guarda, come arriva? Okay, sorry. This random measure can have regions with a very high mass. Okay. So if I explore the space, the Euclidean space RD, usually, I can find very big time to time. I can have very big fluctuations in the going towards infinity. So I wanted an ergodic theorem trying to control this, showing that without any additional assumption, we have some control at infinity. Therefore, I used test functions which are not with compact support. So let me give this definition. So let us take a continuous function on Rd. Then I say that this function phi is good if for some positive constant and for an exponent beta bigger than 2d plus 2, I have that the modulus of phi decays at least as c times 1 plus the modulus of x, the norm of x, to minus beta, and this for each x. And then I have this theorem. So consider the previous setting where I have a random measure and I have the covariant relation. Then, so if the action of the group on the probability space is ergodic, and if the intensity is finite, then for almost all omega in the probability space, given any function good phi, so simultaneously for all phi, it holds the following. So if you consider the integral of this observable with respect to the risque random measure, mu epsilon omega, so this integral, which is a random integral, is a random object, it converges to a deterministic value given by m, so the intensity of the random measure times the integral of the observable with respect to the Lebesgue measure. So in particular, this theorem also, for example, if you take a phi in the Schwarz space. Okay, let me give some comments. So for simplicity, I've stated the theorem in this form, but it covers more general cases. And of course, you can always invoke monotonicity, that is, if phi is upper bounded and lower bounded by functions, which are good, then you can apply the ergodic theorem to this psi n prime, and you get the ergodic theorem for phi, if phi is the pointwise limit of these functions. Okay, just to say that it's not necessary that the phi is really smooth, it's really continuous. Now, this theorem is related to the abstract ergodic theorem with weights I have produced and I've shown you before, because it comes, so it's an application of the general ergodic theorem with weights, where the function f evaluated in the element of the probability space is the following. So f of omega is the mass given by the random measure to the fundamental set. Therefore, in particular, so if you, on the other hand, you before having this theorem, so I applied the Tempelman and Schulman's ergodic theorem, but in order to have the ergodic theorem for the random measure with this function here, essentially, then you have to require this extra condition, because you need that f, the function f, is in LP. And this means this is the condition that f is in LP with p strictly larger than 1. In my case, for my theorem, I just needed that f is in L1. But saying that f is in L1 is the same than saying that the intensity is finite, and this was indeed my condition. Okay, so I don't. So this theorem avoided this additional condition, the theorem, the ergodic theorem with weights. It's true that if you apply the Tempelman-Schulman theorem, then okay, you can cover more functions. That is, the polynomial decay is with exponent beta, and beta is just larger than v. So I don't think that my exponent is the optimal one, and probably one could, working harder, could reduce the exponent. And I mentioned also that if one just use the multidimensional ergodic theorem, then the previous theorem can be proved. So it's known for phi, which is continuous with compact support. So my problem was to extend the result to phi which have some decay at infinity, but not with compact support. And I will show soon the motivation. Okay. So, so let me know if there are questions. Otherwise, I continue with the third part, which is my initial motivation. Okay, so I've shown you an ergodic theorem in the abstract setting with weights. I've shown you an application, which is an ergodic theorem for random measures. And this ergodic theorem for random measures has application to homogenization, to transport in disordered systems. And indeed, the story starts from this, at least my story. Okay, now there are many models to study transport in disordered systems, but okay, one very much used, so it's not the only one, but modelization, very common modelization is to study transport along random graphs with weights. Okay, so now my starting point is the following. So I have a random weighted graph. So again, all our stories start, all our tales start with the probability space. So I have a omega FP, a probability space. And now I call the elements of this probability space environments, okay? Because they describe in the application the medium, the disordered medium, where transport takes place. So in particular, so my environment describes all microscopic sources of randomness. And for each environment, I have a graph that I denote by G omega, which is a weighted, undirected, that is non-oriented graph in RD. Okay, here you can see a picture. In this case, I have color edges instead of, so the colors corresponds to weights. So I fix this notation. So I denote by omega hat the vertex set of my graph. So in my case, the omega hat here are the vertices, so the black points in this picture. Okay, and then I denote by C, X, Y of omega, the weight, also called conductance, associated to the age XY of my graph. So this is a positive number. So edges have a positive conductance. Now it's better to simplify the formulas to extend, to use this convention. So I assign conductances also to any pair of vertices, CXY, but the conductance is 0 if X and Y is not an edge, okay? Okay, there are so here you see a picture, and I can show also there are plenty of models where of random weighted graphs. So in this picture, you don't see the colors because it was too much demanding, but you can think to a standard deleted CD with the weights or some percolation graphs with weights, or you can pass to continuum model. For example, this is a Boolean model. This picture here is the previous one. So it is the dual graph, the graph dual to the Voronoi tessellation of a simple point process. But you can consider also very wild things. For example, you can realize a simple point process, or take a realization of a Poisson point process or any other your favorite simple point process. So you have a random set of points in RD, and then you take the complete graph on this set. Okay, this, of course, in the simulation is done with a finite number of points, otherwise it's impossible. And you have, moreover, you can add weights. Okay, in this case, I could, for example, here consider that all weights are equal to 1, but you can also randomize the weights to the edges, and so all these pictures could be colored. Okay. Now, when you have a random weighted graph, you can, there are very often in physics, there are two approaches to study transport. One, sorry, I was too fast. I will come back to the two approaches, sorry. Okay, let me go on with the setting. So I have this random weighted graph. And I have the group, the action. So I have, again, my group, I can work with the group G equal to ZD or the group G equal to RD. And the group G acts on the probability space, and the action, I call it theta J. So I remain abstract because the actions, as you have seen in the previous examples, although they were for random measures, actions depend, so are model dependent, but they, so the precise form. On the other hand, I have the action of G by translation, and as before, I consider translation of this form. So tau G is the translation sending the point X in X plus VG, where V is a fixed invertible matrix. And the paradigm that I want to formalize is the following. So theta G of omega describes the updated environment when we perform a translation tau minus G of the medium. The fact is that the environment at the end is given by the macroscopic sources of environment, coins or dice and so on, roulette and so on. And the idea is that you translate all these sources of environment when you translate the medium. So the sources of environment are attached to the points. Okay, and okay, now I have, so this is the longer slide in my talk, but although it is longer, because I have six assumptions, I just want to stress that these six assumptions cover a huge number of models, in particular, all the models I mentioned before with the pictures where you see the Boolean model, percolation cluster, percolation, so the complete graph and so on. The assumption, so it's a huge class, and I fixed some very basic assumptions. So I assume the idea is that my medium is microscopically disordered, but macroscopically homogeneous from a statistical viewpoint. And this corresponds to this property, that P is stationary, is G stationary. So it's left invariant. So the actions of the group on the probability space is given by measured preserving maps. And let us assume also that P is ergodic. Then, okay, given my graph, given the environment omega, I can associate to omega a measure, which is simply given by the sum with X vertex of my graph of delta X. So it's a bijection. It's the same content of information of the vertex set. And I assume that the intensity of this random measure is finite. Okay, here also positive. If it is zero, it means that there are no points almost surely. So the graph is stupid, it's empty. And then I can formalize the paradigm I showed you before, this paradigm here. These are words, but in order to formalize it, there is a mathematical way, and this is this covariant relation. That is the weighted graph associated to theta G of omega, so the action along the group element G of omega is equal to the original graph associated to omega, but physically translated physically by the Euclidean translation tau minus G. And this is identity of weighted graphs. Therefore, it's both an identity concerning the vertices and also an identity concerning edges and their weights. And the identity concerning the vertices is exactly the covariant relation for mu omega I show you in the second part of my talk. Okay, and then I assume that the graph is connected, pure not surely, but this can be relaxed. Then in order to use two-scale homogenization theory, I assume that the space L2 of P0 is separable, where P0 is a band distribution. Okay, I don't want to introduce it. Let us say that roughly P0, at least when the matrix V describing my translation is the identity matrix, is the original probability condition that the origin is a point of the simple point process. And then I have this moment condition. So lambda 0 and lambda 1 are integrable with respect to P0, where lambda k, for k equal to 0 and 2, is defined in this way. So P0, recall typical omega for P0 satisfies this condition. So the origin is a vertex. So I sum among all vertices of the conductance between 0 and x. Recall that by convention, this is 0 if 0x is not an age. So I have the conductance time the norm of x to k. So when k is equal to 0, this lambda 0 of omega is just the total conductance exiting from the origin. So I have but the condition that lambda 0 and lambda 2 are integrable with respect to the Planck distribution. And these are my assumptions, and there are plenty of models satisfying this assumption. Now, as I told you, there are two approaches. You can think two basic approaches in order to study transport. So one is given by resistor networks, but I don't consider, so this was treated in another word. And the other is by random walks and interacting particle system. So let us consider just one particle for simplicity. So I consider the random walk xt omega. So the state space, so this is a random walk on my graph. So it lies on the vertices of my graph, and it is continuous time random walk, jumping from one vertex to another vertex with a probability rate, which is the conductance of the edge. So it jumps only between nearest neighbor edges in my graph. Note that the graph can be also with very long edges. Okay, and under my condition, this random walk has no explosion homogeneity, and it's well defined. Okay, and then let us consider some scaling property, last scale property of this random walk. So I consider the random walk, but rescaled diffusively. Okay, and I call L epsilon omega the generator. Okay, and then I obtain this result. Yeah, I am a little vague, but okay, soon I will show you something more precise. So for each environment in a set of typical environments with probability 1, we have homogenization for the massive Poisson equation. So I consider the Poisson equation with gamma positive, gamma u epsilon minus the generator, the diffusively rescaled random walk applied to epsilon equal to f epsilon, towards the partial differential equation, gamma u minus divergence of d gradient of u equal to f. So here, u epsilon and f epsilon are in the space L2 with respect to the rescaled measure, mu epsilon omega. Recall that I have associated to the vertex set this measure. So a combination of Dirac measures on the vertices. So you rescale this measure. Okay, and vaguely it means that if epsilon is near to f, which is in another space L2 of the MDX, then the solution u epsilon is near to u. And in this equation, D is the so-called effective homogenized matrix. It comes from homogenization theory. It has a variational characterization, and I don't enter in the details. But what I want to show, okay, to conclude, I'm very near to the conclusion, is this fact. So, as I told you, this solution works. So this u epsilon and f epsilon here, they live in this space, in this L2 space, while u and f live in another space. So what does it mean that their u epsilon is near to u? Okay, this is a concept in not new. It means the following. So you can say that V epsilon, so a generic V epsilon in this space, converges to V in a macroscopic space if this family is bounded, at least when epsilon goes to 0. And if you take the scalar product of V epsilon with the test function phi, which is continuous with compact support, this scalar product in the associated L2 space, this converges to V scalar product with phi in L2 in MDX. And okay, you can also define a strong convergence by taking now not a fixed text function, but you replace here and here that you test against sequences, weakly convergent sequences. So if your family, V epsilon, W epsilon, were in the same space of V and W, so all L2 spaces are the same, from here you would get the standard convergence in L2. And so if you apply, so there is a lot of work to get the homogenization results. But so if you just restrict to homogenization by two-scale convergence, so you get the following. I got the following. So I have that the Markov, under my basic assumptions I showed you before, the slides with the 6 assumptions, I have that the Markov process, the Markov semigroup of the rescale random walk converges in this form to the Markov semigroup of the Brownian motion with diffusion matrix 2D, and the same hold for the resolvent. Okay, it's a weaker form of convergence, but you can enhance it if you have some control at infinity of the random measure. And now the stories of the circle closes because both these limiting function decays fast at infinity. They are not with compact support, but decay fast at infinity. So by combining the previous homogenization result with the ergodic theorem I just shown you, you obtain a convergence in a much stronger form, in norm, in this both in L1 and in L2. Okay. And this convergence was obtained in the paper where I study homogenization by an additional condition called A9 there. And the fact is that at the end, this condition is not necessary anymore because you don't need, thanks to this analysis, investigations that I had concerning the ergodic theorem for random measures. And now I conclude by saying that, so why we are interested to this kind of convergence? Because they are at the basis of the proof, for example, of hydrodynamic. Okay, they are already a form of central limit theorem, but this is exactly the form that you need, for example, when you want to prove the hydrodynamic limit of the symmetric simple exclusion process. So let's consider, this is my last slide. So consider now the symmetric simple exclusion process on G omega. So multiple random walks, not just one, multiple, many of them as before, but with a site exclusion. So if a random walk attempts to jump to a site which is occupied by a particle, then the jump is does not take place. So here I've written the generator, and I suppose that all people in this audience knows interacting particle system. And so I have this theorem that for P almost all environment under diffuse space-time rescaling, this interacting particle system, the set set on the graph has hydrodynamic limit in path space described by this equation. And okay, with some more assumptions compared to my assumptions here, the result was obtained in this. I obtained the result here. But by combining other intermediate results, in particular the ergodic results presented today, I was able to remove the assumptions, and for the theorem now holds with the same conditions, the same assumptions I present in this third part. So I conclude here there is a bibliography. Okay, I can also share the slides if you are interested. This is the paper of Tempelman and Schulman, and the results I've mentioned are here, in particular the ergodic theorem is here. So, okay, I think that's all. So thanks for your attention.
Okay, thanks a lot. Any questions? No, okay. If when people think about them, I have Milton.
Yes, so I have a question. So about this decay on the test function on your theorem. So
Yes.
so Tempelman can do this exponent bigger than D is so it's basically the threshold on which this polynomial decay implies integrability, right?
Yeah, I think that is, I think So my guess, is that the theorem should be true. So my theorem could be probably extended to cover also the case beta bigger than D. This is the natural condition. 2D plus 2 is a technical condition. Yeah, I agree. But the fact that I was motivated by this application, so this function here, they decay faster. So
Right.
they decay faster than any polynomial. On the other hand, by using Tempelmann and Schulman, I had to impose the assumption that my simple point process given by the vertex set has not only a finite expected number of points in a given finite bounded volume, but also a moment larger than one, finite moment larger than one. So the number of points, for example, in a box. And this is not necessary. That is, you don't need this. This is the message.
Okay.
So ergodic theorem is stronger. So then maybe what we are more used, that is, it allows to control fluctuations at infinity, at least in a weaker form, but enough for me because I had to treat this.
No, anyway, I find it very interesting because it's this is usually a difficulty when you look at the ergodic theorem, right? That you cannot really take this. You always have to somehow work in a bounded domain because I mean the club. This is the sort of classical limitation of the ergodic theorem, right?
Yeah. I have to say that if you take, for example, the book of Krengel, so there are some Bibles in ergodic theory. So there is the book of Krengel, the book of also Tempelmann. There are some forms of ergodic theorem with weights, but they were not good enough for my applications. So there are also, so in the literature, there are some, especially if you work not with the group CD, but just as in Birkhoff ergodic theorem, when you have just a map T, and you consider, so in Birkhoff ergodic theorem, you have a measure preserving map, and then you take this average, no, I cannot write, okay, F of T J omega. Okay, here, so there are results, especially in dimension 1, when you put the weights here instead of 1 over n, and you have some decay. Okay, in this case.
Okay.
Okay. Further questions? Okay, if not, let's thank Alessandra again.
Thanks. I also wish you a nice Eastern holidays, vacations.
Thank you.
Thank you.
And thanks again.
Thanks.
So I do not know how to stop sharing. Okay. And if you need to upload the slides, I can give the slides. It's the presentation, the PDF. I can send. Ines, I will send you the file.
Okay, thank you. I have
okay.
Everyone's gone, and this is unofficial. But what kind of example were you thinking about when you say that you do not have a higher moment than one, for instance?
What? Can you repeat? I didn't hear well.
Yeah, for instance, when is it that you don't have a higher moment? What are you thinking of? What kind of example?
With the final moments for the simple point process?
Oh, yeah.
Okay. That is, it should be something very pathological. That is, so if you have I think that if you have an ergodic translation invariant simple point process, then if I remember well, so if it is ergodic, then you should have a finite intensity. If it is ergodic. Probably one can build some. So that is, if you, in order to build a simple point process with infinite moment of for example, the number of particles in a box is simple if you don't require ergodicity, because you can take a superposition, so a linear combination of standard simple point process, and you put so the weights in such a way that the mean intensity is infinite. For ergodic simple point process, if you impose ergodicity, I would have problems to build a counterexample. If I remember well, maybe they don't exist, because yeah, I have this impression, but I should check. That is, I didn't explore these counterexamples.
Okay.
So I'm not so sure what is my last statement. So it's unofficial. So was it on YouTube also? This was it recorded? Because no, it's better if the recorded had stopped before. Okay, my memory now is weak, so it's at the end of my day. I wake up at 5 a.m. usually, so the end is the working day is finished for me. It's finished.
It will not be recorded.
Okay.
Don't worry.
Okay.
Thanks a lot.
Okay.
Yeah, happy Easter to everyone.
So thanks everybody. Bye bye. Ciao Nina, ciao Pablo, Milton. So I saw a lot of people that I know. Okay, no well. Bye bye. Ciao, ciao.
Hi Nina, I didn't see you before.